First of all, thank you very much for being here. This is my second time at CyberCamp. I really like it because you get to meet so many people who are curious about everything and are willing to learn. And that's the best thing you can take with you. You share ideas, and that's interesting. As it's been said, I'm an IT engineer. I've working on pen testing all my professional career. This is my presentation. Maybe you know me because I've been part to Munda Haka. This is a TV series. And my professional life has revolved around pen testing and hacking, offensive hacking mainly. But ever since my school years, I've been interested in artificial intelligence. What happened? That was 2003, 2004. There were not many options to work on that. But then 2010, 2011, that's when I started hearing this word. That was big data. Could someone define big data? Does it ring a bell? Have you heard it? Hands up. Yes. And of you, this one, you, the one closest to me, can you define big data? That's right. I will repeat it. Big data would be algorithms and architectures that will let me process large amount of data in an efficient and fast way. I was hearing that name more often and my interest grew. And I realized that big data was closely related to IA that I've so very much enjoyed in my school years, but I could not define. I will look into it. I got all the papers I could find. I got my certificates. And so it started growing on me. And machine learning algorithms, IA algorithms, were being used in the defensive security sector, not so much on the offensive side. And that's what I wanted to bring here for my agenda. Scientists say that deep learning, the basis of my presentation, will be the future for Silicon Valley technology. So what's the basis here? What will I explain here? First, let me tell you why you should be interested in deep learning. You might ask, well, I'm not interested. This is the first time I hear about it. I'm not interested at all. But we will see why we should all be interested, finding out what this technology is about. Then we will move on and see what a professional working in this technology does. So what's the life cycle for machine learning? Because I will be referring to different concepts here, but as I go in deeper, I will define them. And I will show you how to work with that kind of technology. Next, brief introduction to deep learning. That's neural networks. When we say deep learning, these are artificial neural networks, or pathways. Once I've shared it all, we will have the basis and the knowledge to understand what is being done. Then I'll explain a specific type of deep learning that is supervised. And since we need some movement, we will run a demo using this supervised deep learning to spot bank fraud. When we buy on the web, such as there are card companies such as Visa or MasterCard that are interested in those kind of technologies. You should know about them as well, because it's not a technology for the future, but it is current. If you're still not too bored and I have time, I will explain unsupervised deep learning and autoencoders. And again, we need to get our hands dirty. That's what's interesting. We need to be practical about it. And we will see a demo on how to use autoencoders, these other deep learning neural networks, for cancer prognosis or prediction. We see it as defensive, that is fraud detection. And then something else And that is, and this other side would be that these technologies are helpful in the medical field. Why are we interested in deep learning? Here you see Bender handling notes, but it helps us take better decisions. If we are not CEO at a large company, we might not care, but let me explain some use cases where the technology is used for these neural networks or AI. Hands up. Have you ever Googled today? Hands up. If you've Googled anything today, if you've gone into Facebook or Twitter? No one? No one's been to Twitter today? Oh, great. I love it. Basically, we're interested. So I have some candy to bribe you, by the way. I will distribute it later. I thought of getting something better, but I missed my train. I didn't have time to buy anything else. We are interested in this technology because Google, Amazon, Microsoft, Facebook, or similar large technology companies are investing most of their capital into further developing this kind of technologies. And these large technology companies are the one moving most of the data available on the internet. And if they are using those technologies, it means that they have an impact on you. And why is that? Because you go to a job interview and HR will be using information, big data that I mentioned, and all the AI algorithms to take a profile of our behavior. Another use case, insurance company, whether medical or risk insurance company, in the end, they use this kind of machine learning technologies as well to do what they call sentiment analysis. They profile our behavior. They same as profilers, FBI profilers for behavior. These algorithms work even better. Last year, I showed how this kind of technology could be used for crime prediction. In San Francisco, Chicago, and other US cities, they are using deep learning, which I've not defined so far, which is just an abstract, is a buzzword. But this has been used by law enforcement bodies for terrorism and crime detection. There's been officers going to different homes saying you are subject of an investigation because you are suspicious because of these kind of movements. And movements have been detected by these algorithms, getting data from different sources, IoT and street cameras, comments, searches, cell phones, Wi-Fi, and Bluetooth when it's on, or telephone antennas that record where we move around. That information has been stored. I actually started working on a project that was aimed at malls, shopping centers, where there would be beacons all over the center, the shopping center. This would be Bluetooth and also Wi-Fi beacons. And with those probes and the Bluetooth cars, they would start identifying us. So in the end, with that information, we would see where the users were, how much time they spend in every area of the shopping center, if they ever came back, at what time of the day, how often they would come back to the shopping center, and those would be behavioral patterns. These are used in every single sector. As I was saying, for one of the demos, will be used for medicine. Medicine is also highly benefiting from this kind of technologies. And why is that? Well, there's some pictures there. First one is the way a deep learning algorithm would behave. Even if you don't see it, there are some black spots. Red spots could be fraud cases. Black could be regular, proper transactions. And so the deep learning algorithm can tell apart one spot from the next, one dot from the net. So it really adjusts or accommodates to understand what's fraudulent and what's not. So it can be curves, and it extracts all the features so that we understand whether a transaction is good or bad. This is a traditional AI algorithm. This is also machine learning. I will not dwell on that, but this is a bit more traditional one. And it is outperformed by the first one. Fraudulent transactions cannot be told apart so easily. Here, random forests, decision-making trees, is another kind of AI that it's outperformed by all others. You see that there is a mess here. This is a linear regression using lines to tell apart one kind of examples from the others. So the performance is even worse. The kind of AI at this presentation will be the best performing one because it's the one that accommodates the best. This is a case of a traditional algorithm, which is the one where you have different features to define a problem. If it's fraud, that would be some features. Those are kind of predicting factors for a fraudulent transaction. When you get many of those predictors, such as name of the car holder, place of the transaction, amount, when you've got many of those, you use principal component analysis technique to narrow them down and keep only those predictors that actually have an influence on the nature of the transaction. It might look like a mess up. It seems that it cannot be fully narrowed down. You see all the dots blend together. These are autoencoders, and they are really good at telling them apart. Each color is a different kind, and it really helps make better decisions. And that's why large technology companies are investing such high capital into developing this kind of algorithms. Google has this technique I find or a strategy I find interesting. They publish all research papers they have, all of them, free of charge. They've got one on nature, on a powerful and neural networks evolution, and it's all made published. It's all about monetizing, and it would be about leasing space on the internet to train algorithms. I'll explain what algorithm training is later on. What I wanted is to show how important this is, and something else I wanted to share, that last summer APA had the Cyber Challenge. Does it ring a bell? And the idea was to have a contest and kind of capture the flag, but it wouldn't be auditors or pen testers hacking the challenges. The idea is to have data scientists developing AI algorithms that could hack. So it's not people hacking anymore, but the hackers are the AI algorithms themselves. So within 3-4 years, the ones doing reversing, it won't be a person. There will be AI programs, predictive programs that can work on reversing and find and exploit vulnerabilities, as we saw from previous presentations. So it's a change in paradigm that will mean that we will, for example, need a basic salary, universal basic salary, because we would have self-driven cars. So either we recycle jobs or we'll have some problem. There is some discussion there. I wanted to highlight it because I guess these technologies are quite important. So I have a video. This is a Google algorithm so that you see its power. This is a reinforcement neural network. When you learn how to do something and you do it right, you get a reward. You are reinforced. So we use this for gaming. So This is the algorithm. It starts from scratch. The only thing it knows is what they find, it finds on the environment. You see it not very good at it, and doesn't score much, so doesn't know what to do. But as they have, it has more scores, it gets points, it gets a reward, and it learns how to do it better and better, faster and faster. The ball is caught more often, and they just do it. It just do it just by what it finds on the screen. No standards have been defined. Just tries and see where the rewards come from. And after over 100 minutes training, magic happens. So strategies are developed. So there would be a tunnel here, as you can see. To place it in here, it starts rebouncing and it scores. It is learning strategies as a regular person would do. So this kind of algorithm tried to simulate our learning method, people's learning method, but translate it into IT algorithms, computer algorithms. Now that you've found the context for it all, let me show you how it works when you use this kind of algorithm. Usually, what we do is we get a history of data. If it's fraud, you see all the bank transactions, and every transaction is a data set that we visualize as table with rows and columns. Columns are car holder, transaction date, amount, where it happened. So regular data. And then rows will be values, examples. These are the kind of data we work with. These are the data that will help the algorithm learn. With those data, we have feature engineering. So we clean them because they are full of shit when we get data from websites or sensors. Usually we get lost values, we get doubled values or duplicated values. There are even mistakes in columns that can be excessive or give us similar information, and just one column would be enough. So we clean it. And this part of feature engineering takes us 70% of all the time. That's proper cleaning of data. Then we divide it into 3 sets, right? Training, validation, and test. This one gets 60% of the data, 20%, and then 20% each, depending on how you want to use it. And let's focus on the training set. Why is this useful? This will help us get the examples. So here we see bank transactions, and per example, per row, we tag it to see if it's a fraudulent or regular transaction. Same as learning with examples. This is what's known as supervised, surveilled machine learning. So we define a value set for predictors, and we say that for that kind of values, whether there is fraud or not. Fraud would be the target or the variable to predict. So we set an example and explain how to behave for those examples. It is example-based learning, same as if we were back in college and we were getting ready for an exam and we would check out exams from previous years. We would see the typical problems or exercises, and we would say, well, this is a typical problem and it's solved this way. This is what happens here. This training set will be transferred to the machine learning algorithm. Here we set hyperparameters, which means that the training, the learning process will happen faster. We'll see what they are all about. But this is kind of magic. There are some buttons we can push so that it learns faster. Once we've past this training data, there will be a predictive model produced. There will be a model that can get new untagged data without saying whether it's fraud or not, and it will reply whether it is fraud or not, which is in the end our target. Same with the same demo here. There will be a series of markers that will explain whether there is cancer or not. It generates a predictive model, but we still don't have a clear way to see if that predictive model works right or not, or if it's a poor predicting method. So to understand whether we are good at it or not, we will try it out with a validation set, which has been tagged as well. So the predictive model has the rows for the validation set, and the predictive model will say whether for this set it is a fraud or not. And since this has been tagged, for every row we know whether if it's fraud or not, and we compare it to what we need to get. Is it clear? Is it too messy? We need to compare whether there is proper prediction or not. And this will help us change it, correct behavior, and to fine-tune training. Once we have properly trained the AI algorithm, once it's fully perfected and we have a predictive model that it's good enough, we try to see whether it can be widespread. There will be another run to see if we can use it for production, for which we get this data set that it's tagged. When I say tag, I mean that for every data set I know whether it's fraud or not, and we give it to the system and see whether it can be widespread. We'll see whether the final model that I produce gives me back a good result and compare it to the real result. And with different measurements, I will see whether it is easily scaled up or replicated, whether it can be used efficiently. And then you use this model. And that's the way to work with this kind of algorithms. You train algorithms to generate predictive models that get untagged data. And with those models and data, they can give us forecast prediction for automated driving, where you use neural networks that highly simulate the visual cortex, same as with any other field, classifiers or automated players that learn how to solve problems. This is being used especially for traffic jam problem solution, to explain how signs and lights need to move to make sure that there is no jam, for any kind of problem you can think of. I've explained a few use cases so far. Let me explain what's the basis for our AI, and that's deep learning, which is based on neural networks. In order to understand neural networks, the basics would be, let me explain you what a regular neuron looks like. This is the picture. There is some dendrites, that is the infit, and the stimulus goes in this way. Said stimulus going in through the dendrites goes to the soma, to the cell body, where the information is processed. And once processed, the information goes out this exit channel, that is the axon. And from there it goes to the dendrites of another neuron. This way, we have a neural network. And the connection of an axon and the consecutive dendrite is the synaptic connection, and the strength of the connection is what helps people, makes people learn one way or another. So our neurons have a given strength, and depending on the strength, we remember something or not. And by joining together lots of neurons, we get a biological neural network. once we have it, what we want is to export it into an IT system. Let's try it. This was done with this artificial neuron that is known as simple perceptron. Actually, it started out in the 40s, moved on in the 50s, 60s. It was promoted in the 80s. But the problem is, well, if it started out in the 40s, why are we hearing about it now? How come that it's technology companies that are investing into it now? Because, it's older than all of us together. For neural network training, you need lots of data, which we have now because of big data. And you need architectures to process information in a fast, efficient way. Hadoop, Spark, does it ring a bell? But those are big data architectures that help us process all those data, running parallel and efficiently. So all those data we produce with social media, cell phone use, and the IoT, with this kind of new architectures, it's making it possible for this kind of algorithms to be used and implemented. You need to realize that up in our brains, we've got millions of neurons. It is amazing. And we're trying to get somewhere near it. But we're so far away still. It's still just starting research. So we are far from imitating a human brain. It is tried though, like this. As I said, the entry channels are dendrites. Dendrites here. This is X sub 1, sub 2, sub L. That's the nervous impulse, the pulse, all the features. It would be the car holder, the amount. That's the entry into what's entered into the neuron. That makes it all the way to the dendrites, as I was saying. And when that neural pulse goes to the dendrite, there is a synaptic connection or linked that has a weight. And our artificial neural network will learn one way or the other based on the amount of those values. So we want to train our artificial neural network so that it finds the appropriate W values so the neural network behaves as we want it. So the target, you need to remind, is getting the right values for weights, and this is all achieved through training. So every X sub 1 we multiply by W sub 1 all the way to sub N, and those weight entries will make it to the cell body or soma, and here we add it up. So we multiplied it and upload it and add it all up, this one, and then we add B. B stands for bias. It would be a threshold we set, or something like a barrier that we set up, so that the neuron finds it easy or not so easy to fire. So it will fire, it will be aroused, and it will return value 1 easily. If values are very negative on the bias, the neuron will find it more difficult to fire, to have the light go on. And with this bias and weight values, we will play around so that our neural network learns the way we want it to learn. So it's all about playing around with values. So with this formula, we get it out through the axon, through the exit channel. But before that, we use a firing formula. And you might say, way too much. Why do we need it? Well, we need it because the firing formula narrows down within an interval we find useful the result, the exit value. Because if the neural network can work with any kind of number, it'll be much more difficult in the end, we'll see it later, to train it. It will be way easier if we find a well-defined and limited value set. 1, 2, 0, -1, +1, -5, +5. But if we narrow down potential results we will find it way easier to find the values for W's so that the neural network does what we want it to do. Before you rush out of this room, let me explain you some firing formulas. I'll explain those because I will use them in my demos, and it's interesting so that you know what it's all about. First one is sigmoid firing function. So the exit, the output is somewhere between 0 and 5, and this is the formula. And we see the output, it will be from 0 to 5. And this is, and 1, sorry. And this is the graph. So we work within a range that could be interesting. But this sigmoid firing function was outperformed by the hyperbolic tangent line that narrows down to -1 plus 1. And it is centered around 0. So it is more interesting to use this based on different problems. And this hyperbolic tangent line is an escalated sigmoid function. This is the one that we multiply, and so it's narrowed down between -1 and +1. But then in 2014, one of the most used firing formula is this one. I removed it. Well, it would be ReLU. It's one of the ones I used. And we'll see, this is the state. If the activation function is below 0, result is 0. If it's above 0, the result is the value itself. And why so much used? Because this is the activation function that looks most like the one that our neurons use. That's the way our neurons fire when they get a stimulus, following that graph. So if the fit is -0, returns 0, and if it's positive, returns the value itself. I've explained already the architecture of the artificial neuron, the simple perceptron. But how does it learn that perceptron? This is Frey. You see if you agree with Frey or not. Well, what we do is we use an algorithm known as gradient decrease algorithm. If you're working on AI, it's quite common. This one is used to handle all those decisions I said already. Car driving, medical questions, everything. So it's good to know this. It starts with T sub 0 with a randomized setup of weights. I want to find the right value to the weight so that our neural networks do what we want. We start with this randomized one, and it can be bell-shaped, but we have that starting randomized, and this would be it, right? And we need to have an error function defined to know how much a mistake our algorithm is with the predictive model. As we said it, we change it into a predictive model, which we need to have a way to understand when it's making a mistake. And this is an error function, this one here, this one. And we need to minimize the error function. The error needs to be as little as possible. So we are here, starting point of the weights of initial value, and what we need to do is calculate the direction where the error will grow the most. We would calculate that. How do we do it? We use what's known gradient for the error function, so that's the derivative. So this is a function, an error function, telling us when there is a mistake, and we need to know where it grows the most. starting here, and this is calculated through the derivative of z function. It would be the slope or gradient of the tangent line to the curve. Back in high school, derivatives were studied, and what's the point? Well, derivatives help us now develop algorithms making decisions that have an influence on our daily lives. So quite important. We calculated the error function gradient. It would be this straight line. This is the slope. And what we do is update those weights following the opposite direction to the largest point, or where it grows the most. So it would go downwards. We would go downward and update weights. So these are the new weights that would equal the weights available now, plus here you see this is the alpha learning constant. That would be the step that I use, or rather the gap, the play. So, and we add the error function derivative for those weights. This way we get the new weight that will be somewhere around here. And so the goal would be to reach this point here, which is the point where the error function is the smallest, where the error made by our function is the smallest. Had we started here, we would have gone down and down and down all the way down here. This is called a local minimum. So it is not the smallest minimum for the error function, because this is a smaller one, this one here. But there are some techniques, such as hyperparameters that I mentioned, that will help us reset it and go down here all the way down to the global minimum value. The minute we get this is the smallest value. That's when our algorithm will know how to do what we are interested in. We need to minimize the error function, to minimize if we are really mistaken in our predictions. You're holding up quite well. I've shown you a neuron so far, an artificial neuron, and I go back, not just to one neuron, but several neural networks, artificial networks. We've got different neural layers. First, we have an entry layer, getting the infit, the entry values. So maybe we have a picture that is 256 per 256 pixels, and there is a 09 digit that is handwritten, right? How many neurons do we need for this entry layer? 256 times 256 is the number of pixels. That would be the entry point for the neural network. That would be the starting point of the neural network. And what we want is for the neural network to tell us what's the digit that we've handwritten into the picture. I said it can range from 0 to 9. So how many neurons can we find on the exit layer? That would be from 0 to 9. We're shaping it. We know how many neurons we need on the entry level and the exit level, or layer rather. It is clear, but what about concealed, hidden layers in between? The ones working magic, so that in the end the neural network can tell apart which one is the handwritten digit in our picture. These are the layers, hidden layers. Every layer, hidden layer, we learn from a set of features, a set of attributes, that it's the output from the previous layer. So what does it mean? It's a bit weird, I know, but the minute we move forward throughout the network, neurons will be able to detect features that are a bit more complex. So picture this. First, neurons can only tell apart corners, edges. Then, next layer, silhouette, maybe the deepest ones, depending on how we make them specialized, they can spot faces. That's a feature hierarchy. And it's a hierarchy that it's growing in complexity, and what's most important, growing in abstraction. So as the network moves forward, it works on concept abstraction, which means after training that network for car detection, for example, if there's a Fiat Pana or a Ferrari, it will say both are cars, and a donkey, it will say it's not a car because it's been trained for that purpose. The neural network can get concept abstraction.
And right, and this is what a neural network architecture is. And then I told you about the learning mode of these artificial neurons. And now I will tell you how a whole network of neurons learn by using the technique of gradient descent that we saw before, but this time we will be adding other elements. And these other things are referred to as backpropagation algorithm. And even if these formula look a bit strange, I will explain them to you. And we start off from initial values of random weights. I repeat it again. These are the values that we want to find, the values of the weights. And then what we will be doing is to take that set of training data. We will just get a row of that set of data, of that set of features, and then we will put them through here. They will go through this entry layer, and we will also include the value of the target, the value of the objective for that set of features. So for instance, imagine a bank transaction. Go and say, well, for that bank transaction that is going through here, we are going to tell whether it is legit or fraud. Then the neural network for that set of features will calculate the output. That is to say, it will try to see whether it can predict whether the feature values are fraud or not. And for that, it does what I told you before, that is to say, multiplying the entries by weight, then they are added to each other, and then that's the way it moves forward in the network. And then this is what we saw before for a simple neuron, and now we multiply the weight by the entries, and then we sum it up and sum it up until we reach the entry exit layer, and then we get the result for each of the neurons here. And what do we have to do now? I told you that the network received the entry pattern and it calculated the target value. That is to say, it told us whether this is fraud or not. And therefore, we will compare it with the real value that we had for the set of training values. And we make comparison as we see here on the screen. Let us calculate the error that takes place in each neuron. And we will starting off with this layer, and this time you will understand why it is named backpropagation. We have these values 1, 2, n. These are the values that we have given to it, and then we compare that with the d. D stands for the real value, and take it from there and we calculate, we work out the error. This delta letter is the error that takes place in each of the entry layers. So the value that we should obtain for this neuron minus the actual value multiplied by the derivative of the error function. And then we will calculate the error that takes place in this neuron, in this other one, and this other one. And for me to know what are the right weights, I really want to find out about the error that took place in each of the neurons, because weights are all over the network. I want to know the error in each neuron. So therefore, I want to propagate the error backwards to calculate the errors that took place in these intermediate layers. This will be derivative of the gradient function error multiplied by the sum of this neuron multiplied by this weight plus the error of this neuron plus neuron by this weight. So we are propagating errors backwards. Then we take a look at all the layers up until we get to the start of the network. And now we know what are the errors made on each mistake. And this will help us update the weights and ultimately to minimize the error. We will minimize the error by modifying the weights. And this is how I update it. The new weight of a neuron in the exit layer would be this new weight plus this gradient, which is alpha, which is the learning rate. That is to say, the speed that with which we travel this curve multiplied by the error and by the output. The error of this neuron plus the output generated by the neuron. And this will help us get the new weights. And we do it exactly the same but backwards. And this process will be repeated and you will wonder when do you stop. Yes, because I calculate the errors and I go backwards, and then in the end I end up updating all the weights. And I say, when do I stop going back and forth? Well, in the end, we will be using a metrics for that, whether it could be the mean square, average mean square, and then we calculate this error, we elevate it to the power of 2, then we calculate the error, and then if the result of that root square average is sufficiently small for us, we stop. Therefore, you may go and say, well, this is, you have to be like really, you have to follow your intuition, perhaps. Well, you will stop by the time the probability error will be very small. You calculate the errors, you propagate them backwards so that you can calculate the new weights up until the error becomes small enough for it to be acceptable. And I say medium square root, but there are other ways to calculate this root mean square and to do this. We also use other algorithms. So, for instance, to find out whether back transaction is fraud or not, that would be type of classification. Or, for instance, I don't know, predicting the value of a home which is located in a specific area. In these cases, one of the metrics that is used to find out how good algorithm is the area under the curve. So you may see here a 45-degree straight line. And this is kind of like getting it right out of chance. When you toss a coin, you have 50% chances that to get one side or the other. So these are the 50% likeliness that my algorithm tells me that that transaction is either legit or fraud. We want this metric to tell us that this curve is above that 50%. Therefore, this is the result of a predictive model, and as it says here, this is good. But here in yellow, I don't know whether you can see it, that it tells us that it is excellent. We want that the area under curve is as big as possible, as large as possible. If it is really big, it means that the algorithm is never wrong. This is not easy, but what we see here, the area under the curve, we want it to be as close as possible to 1. And how do you calculate that? Well, there is a formula for that. I wanted to mention that to you because surely you will hear this from people who are into AA. They will talk about true positives, true negatives. Here we say the true positive rate. True positive rate, it's also known as sensitivity. So the rate of true positive is calculated by dividing the true positives. And then you may go and say, what is a true positive? Well, a true positive is when my algorithm tells me that a transaction is fraud and the prediction is correct, divided by the true positive plus the true false negatives. False negatives is when my algorithm tells me that a transaction is not fraud, but it is actually fraud. So we are dividing the true positive by all the false positives. And on the x-axis, we have a positive rate, and we have the false positives. And this is when our algorithm tells us that a transaction is fraud, but it is not actually fraud. So these are the true negatives. My algorithm predicts that it is not fraud, and actually it is not, plus the false positives that I mentioned before. So with this formula allow us to generate, to plot this graph. The bigger the area, the closer to value 1, where the area and the curve is close to 1, let us say 0.9. This tells us that we are on the right path. So, well, acceptable rate 80%, 85%, depending on the purpose of of the neural network. And other metrics that I use for my demo, I just wanted to share that with you so that you don't get lost when you see it, is the log loss. So this measures the lack of certainty of the probabilities of each class. That is to say, my algorithm would assign a priority to each class, to a class of possibility of it being fraud or not being fraud, and then it measures the lack of certainty of those probabilities and compare that to the real or actual possibilities. What happens with the log loss? Our objective here is that that value is as close as possible to 0. Well, before we wanted that value to be closer to 1 with the area and the curve, but now with log loss, we want it to be closer to 0. So, well, I will skip the formula now, and now I just wanted to share first demo for fraud detection. All right. All right, I have to change screens. Give me a minute. So I didn't know whether I could read it well or not. So I just wanted to do a live demo, and I also recorded it on video. So then I will show you the demo on video. Better now. And I will tell you what we do. Okay. So this is an algorithm that will be using everything that I explained with you to say whether these bank transactions are fraud or not. So when someone uses our card to make a transaction, this is what large companies do to detect fraud. Well, I use the following platform, R programming language, and I also use the deep learning library H2O. And this is the set of data banking transactions. Okay, I will slow down a bit. I will stop here. Okay, these are the data that we use. This is a set of banking transaction data. It is very difficult to find this set of data because, well, credit card companies are not interested in disclosing this data. Well, I found this data set which is anonymous. It means that these columns, the features, characteristics, or predictors or synonyms So I refer to as V1, V2, where there is one Stein, V4, V3, very many V letters that have been made anonymous. So the names of the features have been removed. Yeah, but here you will see a last column that tells us if each of the rows is a fraud or not.
Ahí las va enseñando, va a hacer un poco el recorrido.
So we do some parsing. And then the last column is class. If it says 0, it means that that transaction is not fraud, and then if it is 1, it means that it is fraud. So these commands, I do the feature engineering. That is to say, I firstly clean data. I take a look at the data characteristics. I draw a statistic of maximum, minimum, first quartile, third quartile to see how features are distributed. So here we see the number of rows, the number of columns. So this huge number of cells. So this is the data set we will be working with. So the statistic data, the median, the mean, very important information to see how each of features behave, and then this data cleaning. That's what it is time consuming. One of the things that we often do is to detect irrelevant features. And for that, we take a look at those who have 0 variance. If all the values of a feature are very close to 0, that tells us that that feature is not giving any information, because those features are all the time using the same value. We are interested in having features working with different values, so therefore the output is different. So therefore, I eliminate those features with 0 variance. This is what I do with that code. Then I also look for those features that are correlated. That is to say, those features that deliver the same information. I do that through Pearson correlation coefficient as well as covariance, and this tells us that I take two features and then I see if one increases, whether the other one increases or not. That will be a direct linear relation, or if one increases, the other one decreases. That will be indirect correlation. And if I find out that they are related, I just eliminate one of them. So that data cleaning that I mentioned at the beginning is about removing the information that is not meaningful for learning. It is the same as if you are, I don't know, reading a book and then you have your notes and both say the same thing. Well, you take either of the two. So after that cleaning, I build a base model. That's where I do the first training. How would stop it? What do you do first? First, you create the most possible basic neural network. In this case, you cannot see very well. Here we have two hidden layers. We have the entry and the exit layer. The first one has 200 neurons and the other one also has 200 hidden neurons. So I divided as a 60% training, 40% validation, and the remaining 20% for test. And what I say here, epochs. And I say one run over the whole set of data with a very simple neuronal network. I do this run and then I take a look at see where the starting point is. I take it from there and I improve the network. So it's being trained. Here it's being trained. You see this 0% here. I stopped it because it takes its time. And because I don't have GPU in this laptop, I had the computer training, doing the training for a week. Then these are the outputs. And what is interesting for me is running these two lines. This is the area under the rock curve. That helps me for validation. And also here we have the confounding matrix that we would not dwell on it. It could be a bit complicated. But these are indicators that are telling me about the training behavior. This is output information that we are getting from the learning process. And I will be interested in what I get when I get here. We want these values to be very close to 1. The greater the area and the curve, the better, the more accurate my algorithm. And let us take a look at the starting values for the validation set of data, helping us to see how good our validation method was. Well, it is 0.93, very close to 1. Well, the network is doing very well. And then for the test one, it is generalizing very well, 95%. We have only done data cleaning, and our network is simple. It's one of the simplest. And I will stop here to tell you that the data that I used are not balanced. That means that there are many other examples of legit transactions and those that are fraudulent. So when we give them examples about one of the two types of transactions, it will learn to better differentiate one versus the other, and that is not desirable. So therefore, there are a number of techniques that are used to balance that differentiation, and one of them is takes care of undersampling of the majority class, that is to say, non-fraudulent examples. So you look at how many fraud examples do you have. Imagine that you have n number. Then you take n random examples of non-fraud, and then you mix them. And at the end of the day, you have the same number of examples of fraud and not fraud. And what is the problem here? Well, I am reducing the set of data that I'm training. So therefore, well, less example, less lower learning. But another technique that we use is oversampling of the minority class. That means that we will be doubling the examples of fraudulent transactions. And here, this is the minority class. We will be doubling it, and then there is another technique, smooth. It generates and it looks at the distribution of the examples of the minority class, in this case the fraudulent class, and it generates new examples in a synthetic manner. Examples that follow that distribution. It takes a look at the fraud cases and it generates new examples following that distribution, following that pattern. And this is what we will be doing now. We will be inserting those techniques so that this data set is balanced. And let us see if after balancing the data set, the results that the output that we get is better than the prior output. So that model was trained, and I am uploading it for it to go fast. You can do it. Once you train a model, you store it in disk, and then you import it later on. And after loading it, we will take a look at the area under curve. It has improved. It was 93% before, now 25%. And here for test, before we have 95, now we have 96. We are improving. Our algorithm is doing better and better. So I'm finishing the demo. I will forward it a bit. And basically the next thing that I do is what is known as hyperparameter grid. That is to say, a random search with very many parameters. I try different architectures, and I see what is the output of each of architecture, and I stick to the best. I did it with a small network, but the next one would be a grid search. That is to say, testing and trying very many hyperparameters for it to be trained better and faster and earlier. And as I say, at the end, I stick to the architecture that has the best performance. And this is where we have all the hyperparameters. I don't have the time to explain them to you. These are the activation functions that I try. I try mechanisms for it to stop. When the training is not improving, I tell it to stop training. Here we see all the models that have been generated, 14 models here. They are arranged from the best to the worst, and I take the best. And this is what you do with this type of projects. I keep the best one here. And this is now I want to show you the area under curve so that you see the improvement now. Okay, finishing calculating. And for validation, 96%, it was 95% before. And for test, now we have 97%. Wow. It is quite accurate. And last, I predict. Number of predictions to see how it behaves on with regard to the set of tests. Here I point out the most relevant features, the one that have the greatest impact in telling me whether the transaction is fraudulent or not. Because these data are hidden, okay, we cannot really are anonymous. This time we don't have the names, but it will be very helpful to find out about the actual causes, causing a transaction to be a fraudulent one so that we can mitigate them. Here I make predictions, I predict cases, and I say a fraudulent case. Algorithm tells me that it is fraud, and when I compare it with this set of tests, I can see that it is an actual fraud, and then this is class 1. It predicts it is class 1, and here it tells me that this is class 1. Therefore, it gets it right. So we just give him examples of the set of tests, and then we compare it to the real label, and then we see the level of match or the level of times that it gets it right up until we get that 97%. I just wanted to share with you how this could help benefit cancer prevention. So this time you just don't give it labeled cases, you just let it to find patterns. You are not going to tell the system whether it is fraud or not. It will look for abnormalities in the data, and then these anomalies will stand for these fraud cases. In our daily life, we follow patterns. Whenever you go out far from those patterns, that's clearly a fraudulent cause. And I had prepared case for autoencoders, non-supervised algorithms for cancer detection, but because I've run over time, apologies, I cannot share that with you. You have any questions, further information, and questions? As I say, I'll be